The objective of Training Module 13 is absolute, zero-fault energization for electrical grid transmission lines and power cables. This requires executing a precise sequence of testing protocols to ensure total system reliability and safety before live power is introduced. To achieve this, testing procedures are bound by a rigid global reference framework. This includes the International Electrotechnical Commission, or IEC, and the Institute of Electrical and Electronics Engineers, IEEE, which govern global and engineering standards. Materials and manufacturing tolerances are defined by ASTM and NEMA, while ANSI oversees U.S. national standards. For large systems, cable engineering, and specialized verification, the framework relies on guidelines from SIGRE, ICEA, and CAMA. This schematic outlines the reference governance rule. When a project specification, a manufacturer instruction, and a published standard differ, technicians must apply the most stringent approved requirement. There is no tolerance for selecting a lesser standard for convenience. Every reference standard used to justify an accepted result must be documented directly on the test sheet. QA reviewers rely on this strict traceability to verify exactly why a specific result was accepted during future audits. Grid commissioning is an uncompromising governance audit. Maintaining exact documentation and regulatory compliance carries the exact same weight as proving physical electrical integrity. Before analyzing individual cable parameters, technicians must establish a universal safety baseline. These mandatory prerequisites apply universally to all high-voltage tests to ensure personnel safety and eliminate procedural redundancy. The baseline begins with the physical application of lockout and tagout protocols. Technicians barricade the test area and independently verify the total absence of voltage. Following isolation, temporary earths are installed wherever required by the specific test schematic. Technicians must ensure that all non-test phases remain either physically open or grounded, completely neutralizing parallel phase hazards. Finally, safe discharge protocols are mandatory. After applying direct current in any phase test, technicians must use grounded discharge sticks to completely clear stored capacitive energy before proceeding. By locking in these baseline isolation and discharge protocols, technicians can execute tests 13-1 through 13-12 by focusing exclusively on the unique electrical variables, instrument configurations, and required hold points of each specific procedure. Test 13-1 verifies phase checking and sheath integrity. 1 kV DC is applied from a megger at the phase R conductor. The far end switch is closed. Zero resistance proves continuous identity end-to-end. Repeat for Y and B phases. Before the sheath withstand test, a 5 kV DC baseline is recorded for 1 minute. Apply 10 kV DC negative polarity between the metallic sheath and earth for 1 minute per phase. Acceptance requires leakage current below 5 milliamps. This schematic details test 13-2, measuring cable insulation resistance and capacitance. After isolating the cable from bus bars, surge arresters, and connected equipment, the megger applies 5 kV DC for 1 minute to each individual phase connection to record baseline insulation resistance and ambient conditions. Using these identical phase conductor configurations, technicians measure the circuit capacitance. The raw data is converted into microfarads per kilometer using the approved route length and compared directly against manufacturer datasheets and design tolerances to locate severe phase imbalances. Establishing uncompromised phase identity and proving foundational dielectric strength are absolute prerequisites. The grid cannot be subjected to extreme high-voltage stressors until these base measurements pass perfectly. Test 13-3 checks transmission line continuity. The R, Y, and B conductors are shorted together at the far end using temporary links. At the test end, 1 kV DC is applied between RY and YB phase pairs to prove stable continuity without open circuits. A critical hold point mandates the installation and removal of the far end shorting link must be formally witnessed before normalization. This diagram shows test 13-4, evaluating phase conductor insulation resistance. For this procedure, all 3 phases must remain totally isolated from ground at both ends of the transmission line. Technicians apply 5 kV DC for 1 minute, checking phase-to-phase insulation across RY, YB, and BR, followed by phase-to-earth resistance. During this minute, technicians monitor the instruments for sudden voltage drops, unstable readings, abnormal tracking noise, or visual signs of distress. Verifying conductivity and total phase isolation across fast transmission distances requires deep scale awareness. Missing a degraded termination or a grounding error creates dangerous dead zones. Test 13.5 measures transmission line susceptance. A single-phase 220-volt AC source connects across phase pairs, starting with RY, to record voltage, current, and frequency. Using these readings, calculate reactance with X equals 2V over I, and susceptance using B equals 1 over negative JX. Repeating this for all pairs proves if capacitive susceptance is balanced and aligns with design data. Moving from massive line capacitance to micro-level connection precision, Test 13-6 validates cross-bonding at the link boxes. Cable screens are grounded at both ends, far-end conductors are short-circuited, and a 380-volt three-phase generator injects balanced current into the conductors under test. Technicians utilize a calibrated clamp meter to measure the induced current at every specific link box and relevant GIS or GIB location. The measured current must not exceed 3 to 5% of the injected value. Proving that the induced current remains suppressed validates that the sheath cross-bonding links are installed correctly. Precise cross-bonding neutralizes dangerous electromagnetic interference, permitting stable parallel operation. Test 13-7 is the power cable very low frequency high voltage test. Because this applies extreme dielectric stress, it requires setting up a remote exclusion zone with physical barricades and warning signage around the VLF test instrument. This diagram shows the VLF connection. Technicians inject a severe 3UO high voltage into one phase at a time for a continuous duration of exactly 1 hour, while carefully monitoring leakage current trends for any symptoms of partial failure. The acceptance criteria are absolute: 0 dielectric breakdowns, 0 trips, and stable leakage current. Surviving the hour triggers a critical hold point, where a witness must formally approve the safe discharge of the phase and removal of the connections. This schematic details Test 13-8, phase sequence and rotation checking. A three-phase AC supply is connected at the test end. Technicians utilize sequence meters at both sending and receiving ends to read phase rotation simultaneously without changing test leads during the comparison. Any phase reversal, crossed conductor, or labeling error must be corrected. Surviving the intense voltage stress and proving a mechanically identical RYB sequence at both ends guarantees the physical grid architecture is cleared for live parallel power. Test 13.9 measures DC conductor and earth resistance. A micro-ohm meter connects across shorted phase pairs to record resistance and temperature. These readings are mathematically converted to 20 degrees Celsius and normalized to resistance per kilometer. For grounding readiness, auxiliary earth rods are driven into soil at 5 to 10 meter intervals. Earth resistance at the link boxes must not exceed 10 ohms. This diagram demonstrates Test 13.10 for sheath voltage limiter insulation and link box contact resistance. To test SVL insulation, the disconnecting bonding links must be removed first. Technicians inject 2.5 kilovolts DC into each SVL point. The resulting insulation resistance must measure 10 megaohms or higher. Following the test, the bonding links are restored and tightened firmly to an approved torque. A micro-ohm meter then checks the connection points. Contact resistance must read near 0, strictly remaining at or below 20 microohms. A minor failure here can be catastrophic. Leaving a high-resistance contact or loose link compromises macro-level sheath protections, leading to severe sheath overvoltage risks when the grid is energized. Test 13.11 measures sequence-impedance. For positive and negative sequence, measurement occurs between two phases, scaling current from a variable transformer up to 25 amps to record voltage, current, frequency, and angle. For zero sequence, all three phases are connected in parallel and injected with a single-phase AC voltage to calculate C0. This diagram details Test 13.12, extending sequence-impedance tests to the transmission lines using specialized equipment like the Omicron CPC100 and CPCU1 booster. To configure a zero-sequence test, the three phases must be physically shorted from both ends of the transmission line. Technicians configure the V-sense, I-out, and grounding leads, running the test injection to capture raw impedance values. These CPC100 readings are then aggressively cross-referenced against the theoretical, approved system study line model to validate accuracy. Accurate sequence impedance mapping acts as the final technical bridge. It confirms that the raw physical copper and aluminum architecture of the newly built grid behaves exactly as the computerized protection relays and network models expected to. Upon concluding Test 1312, an extensive result and evidence package is compiled for handover. This package mandates the inclusion of all raw micro-ohm readings, VLF leakage trends, environmental temperature conversions, instrument calibration certificates, and formalized witness sign-offs. Regarding mechanical instructions for repairing a component that fails these tests, not specified in the provided sources, refer to project-specific hold point management. This lack of repair instruction is entirely intentional. Commissioning is a strict verification audit, not an assembly phase. If an SVL insulation test fails or a VLF leakage current spikes, the immediate hold point is revoked. Technicians do not invent on-the-fly repairs. The failure triggers an independent engineering review to determine root cause and corrective action. Zero-fault energization is never achieved by chance. It is the guaranteed outcome of rigid test sequencing, scale-aware safety protocols, and uncompromising governance over every phase, sheath, and termination across the electrical grid.